Okay, so you can everyone can hear me, right?
Yes.
Yes.
Yeah. Okay. Thank God. And okay, so I think we can now begin our seminar. So welcome to the IEEE ComSoc SBS ISAC webinar series. So this is a joint seminar with One Word Signal Processing seminar series. So today our speaker is Athina Petropulu from Rutgers University, USA. And I will introduce a bit about Professor Athina Petropulu. So she is a distinguished professor at the Electrical and Computer Engineering Department at Rutgers, having served as chair of the department during 2020 to 2016. Her research interests span the area of statistical signal processing, wireless communications, signal processing, networking, physical layer security, and radar signal processing. So Professor Petropulu is fellow of the IEEE and IEEE and a recipient of the 1995 Presidential Faculty Fellow Award. And she is now a president-elect of the IEEE SPS and a general chair of the SPS and SPS 2020 and 2021 progress workshops. So in the past, she has served as EIC of the IEEE TSP and IEEE SPS VP conferences. She was the general chair of the ICAS 2005 and spoke 2018. She was distinguished lecturer for the SPS for 2017 to 2018 and is currently distinguished lecturer for the IEEE AESS. So she is a recipient of several vice paper awards, including the 2005 IEEE SP Magazine Best Paper Award and 2012 IEEE SPS Maturity Service Award, and she's a co-author with of the 2020 IEEE SPS Young Earth Best Paper Award, and a co-recipient of the 2021 IEEE AESS Best Paper Award. So before we begin Athina's talk today, I would like to remind you again about our Q&A rules. So during the seminar, all the audiences will be muted. And if you have any questions, please type your questions and send them to me. We will collect the questions from both audiences from Zoom and offsite live broadcasting. So during the Q&A, we will choose 3 to 5 questions to ask a speaker. And we will name questioners, and they are encouraged to ask questions by themselves. Okay, so please go ahead. Athina, I will stop sharing, and then you can share your screen.
Hello, everybody. It's my pleasure to be here. I'd like to thank Dr. Fan Liu for the invitation. And thank you for the introduction. Thank you for taking the time from your summer to attend this talk. I hope you are enjoying your summer wherever you are. So I changed a little bit the title. I would like to also summarize my previous work. I hear a lot of echo. Do you hear me well?
Yeah, I can hear you. Yeah.
Okay. I'd like to acknowledge the help of my past and current students, Polly, Shenxiao San, and Zhaoyi Su. And this is work that has been supported by the National Science Foundation and Raytheon Corporation. So there will be 2 parts in this talk. The first part is I'm going to briefly go over the work that we have done on spectrum sharing between MIMO radar and MIMO communication systems. And the second part is on our more recent work, and I will present it in more detail. It's on a dual function radar communication system that uses OFDM waveforms and sparse array. So before I proceed, I will give you some background on MIMO radar. radar find a lot of applications. Probably the most exciting application right now is on autonomous driving. So radar sensors have been widely used in advanced driver assistance systems, ADAS, for example, cruise control and emergency braking. But recently they have emerged as a key technology for autonomous driving systems. They provide an all-weather sensing modality. So currently autonomous driving vehicles have over 10 radar sensors that provide a 360-degree surround sensing. For control critical functions, distant obstacles need to be detected with high angular resolution. And you can improve the angular resolution if you increase the size of the array. But in this particular application, the size matters because you want the array to be integrated behind the bumper on the vehicle. Another interesting application of radar is on remote health monitoring, where it provides caregivers the opportunity to diagnose problems from a distance or monitor the treatment of patients. And the patients could be wearing wearable sensors, but that provide continuous monitoring. But those need to be actually worn, they can be damaged. On the other hand, radar technology is non-contact technology. Also, it does not intrude on people. It's not like cameras that violates the privacy of people. So radar technology is being used for monitoring, non-contact, non-intrusive monitoring. Again, high resolution is required to track multiple individuals. For example, two people to track their heartbeat when they're sitting close by. Now, popular technology for all these applications so far has been phased arrays. A phased array consists of a radio frequency chain, RF chain, that is connected to a number of antennas. Antennas represent analog processing. So there is a single waveform that is weighted by different weights by the antennas. And by controlling the weights, we can focus the beam to a particular direction. So by changing the weights, we scan space looking for targets. On the other hand, MIMO radar consists of multiple RF chains. Each RF chain is fed by a different waveform. And the waveform diversity allows us more flexibility to synthesize wide beams. And this means that there's no need for scanning of space. We can detect multiple targets simultaneously. Another advantage of MIMO radar is the ability to formulate a virtual array. What is a virtual array? We have a number of sensors that transmit orthogonal waveforms. Now, at the receive antennas, each receive antenna, knowing the orthogonal waveforms used at the transmit antennas, performs match filtering. And since we have 3 orthogonal waveforms, after performing 3 match filters, one receive antenna obtains 3 views of the target. So if we have 3 receive antennas, we have 3 times 3, 9 views of the target. So this is what an array of 9 elements would give us. Here we have an array with 3 plus 3, 6 physical elements, and we get something equivalent to having an array of 9 elements. This is what we call by virtual array. So a MIMO radar allows us to improve resolution because the resolution is proportional to the aperture of the array. So it gives us the ability to improve resolution, without increasing the number of physical elements. So in both of the applications that I mentioned, this is an important issue, the ability of MIMO radar to achieve high resolution. This has captured, this is why MIMO radar have been very popular in autonomous driving applications. Right now, the most commonly used modality is LiDAR that depends on light. LiDAR provides very good angle resolution, but is susceptible to weather conditions, and it's also expensive. On the other hand, MIMO radar does not depend on the weather and is not as expensive. So the automotive industry is focusing in using MIMO radar instead of LiDAR in order to get good spatial resolution of the surroundings. So LiDAR basically, because they can achieve a very high resolution, they create these point clouds that can be processed by machine learning algorithms and get very precise picture of the surroundings. They're called, it's like an imaging modality. A MIMO radar can be used also as an imaging radar in that sense because of their high resolution. You can read more in our paper here that appeared in the Signal Processing magazine in 2020. Now, in our work, we used a special kind of MIMO radar, a MIMO radar that performs sparse sensing. So, we noticed that in a typical MIMO radar, the measurements of the receive elements are used to populate a data matrix, either locally or the measurements are sent to a fusion center that populates this data matrix, and this data matrix can be used for target estimation. Now, it's easy to show that if there's a small number of targets and we have a large number of antennas, this data matrix is low rank. This means that it has a lot of redundancy. And actually all the information that is contained in this matrix is contained in a small number of its samples. So based on this, we proposed a MIMO radar that uses sparse sensing, MIMO MC radar. So, instead of obtaining Nyquist rate samples at these antennas, we randomly sample in time, different sampling scheme in each antenna, and we populate the data matrix in this fashion. So we sparsely populate this matrix. And because the matrix is low rank, the missing elements can be recovered using matrix completion. Now, obtaining fewer samples means that we need slower A to D, and if we were to transmit those samples to a fusion center, we would need the lower communication overhead. And matrix completion is basically the operation where you fill in the missing elements in a matrix, and this can be done by minimizing the nuclear norm of a matrix subject to meeting the observed entries. And of course, matrix completion can be done in under certain conditions that depend on the coherence of the matrix. And we develop those conditions. So the coherence of the left and right singular spaces of the data matrix must be bounded by small numbers, the smaller the better. And we found those bounds that depend on the number of receive and transmit elements. And we saw that as you increase the number of elements, those bounds 10-1, which is the best possible scenario, the smallest possible coherence. We also showed how those bounds increase when the targets get closer, which means that you need more samples in order to fill in the matrix when the targets are closely spaced. And now I'm going to use this MIMO-MC radar for spectrum sharing between MIMO radar and MIMO communication systems. I guess I don't need to motivate you for the need of spectrum sharing. Since you're attending this seminar series, you appreciate the need for spectrum sharing. Just to give you, just discuss the potential for interference in the two applications that I already mentioned, the room monitoring application and the autonomous driving application. So currently, for room monitoring, they use ultra-wideband radar that operate at 24 gigahertz millimeter wave band. But this band has been licensed for 5G deployment in most major US cities, which means that soon there will be interference between those radar and your phone if you try to use your phone inside the room that uses this kind of monitoring modality. Also, if you look at autonomous driving, right now, actually next generation radars for autonomous driving will operate in the 76 to 81 gigahertz band, the W band. And while currently for vehicle to infrastructure communications, they use 5.9 gigahertz that allows for 30 megahertz bandwidth. In the future, we're talking about connected vehicles that will need to transmit sensor measurements in order to improve the perception of the surroundings. So this will require a lot of bandwidth. So they're looking into using the W band for future connected vehicles. So again, there will be interference between radars and this communication, V2X communication in the future. So controlling interference and efficient spectrum sharing is very important. And there are various ways to avoid interference, for example, by large spatial separation, but this is not always possible, or by dynamic spectrum sharing, which is not spectrally efficient. And by using multiple antennas, we can do spatial multiplexing. And there were works that did spatial multiplexing, having a primary user the radar or the primary user the communication system. We did some work where we jointly optimized the two systems. So we did the cooperative spectrum sharing, and we used the MIMO radar that used sparse sensing and matrix completion. And we saw that actually the sparse sensing helps in this scenario. So we used this scenario. We have a radar that is trying to detect targets like cars, and we have a cell phone that needs to communicate with a base station. And when the radar transmits, it interferes with the base station. And when the cell phone transmits, it interferes with the received signal at the radar. So we developed a method that basically optimizes the signaling schemes of the two systems so that they minimize interference to each other. So there is a control center that collects information from the two systems and tells each system what kind of signaling schemes to use. And our work received a lot of attention this year. We got two Best Paper Awards from the Signal Processing Society and the IEEE Aerospace and Electronic Systems Society. And I will briefly summarize that work. So we use the MIMO radar that does sparse sensing and matrix completion. And the joint design is so that we maximize the SINR at the radar receive antennas subject to meeting communication rate and power constraints. We saw that the joint design outperforms non-cooperative schemes or partially cooperative schemes. We showed also that the random subsampling at the radar modulates the interference channel. And this allows for the communication transmitter to transmit in a way that it does not interfere with the radar. We also saw that MIMO MC radar can coexist with the communication system and achieve a better target estimation than regular MIMO radar, while saving up to 60% in data samples. So how this work, very briefly, we can look at the receive signals at the radar and at the communication receiver. At the radar, we perform sparse sensing. So this is represented by Hadamard product with this omega matrix. Omega is a sampling matrix, is filled with 1 and zeros, 1 corresponding to the times that were sampled, and WR is the data matrix. And this can be represented in terms of the signal component, which is what the radar is interested in. P is a precoding matrix that the radar will use. S are the radar waveforms. And D is the target response. And then we have the interference term. The first term is due to clutter. C is the clutter response matrix. And the second interference term is due to the communication system, plus noise. If we look at the communication receiver, it receives the signal that is interested in from the cell phone and the interference from the radar plus noise. So G1 is the interference channel from the radar and G2 is the interference channel from the communication system. We can formulate the covariance of the interference plus noise at the communication receiver. Is this function of the interference channel, and phi is the P Hermitian. P is the precoding matrix. If we look at the radar transmits symbols and the sampling changes on a symbol by symbol basis. So if we look at the channel between the communication and the radar antennas, receive antennas, the channel changes on a symbol by symbol basis. So it's time varying. We define the interference as the average of the interference over L symbols. So we can represent the channel here G2L, where L is the symbol index. Now, we talk about effective SNR because we only care about the SINR during the sampled instances. So we defined effective SINR at the radar in terms of all the quantities that we saw before. And the two systems cooperate on estimating the channels G1, G2, and they share those channels with the central processor, which is a controller. And the controller formulates this problem. It wants to maximize the effective SINR with respect to the covariance matrix of the communication system, the sampling scheme at the radar, and the precoding of the radar, subject to meeting some constraints. And the constraints is for the communication system to meet a certain rate, C, and for both systems to meet a power budget. And of course, this is a non-convex problem, but we solve it using alternating optimization First, we solve in terms of the covariance of the communication system with fixed phi and omega, and so on. So the MIMO radar is a special case of the MIMO MC system when we sample at all times. Now, if you look at the MIMO radar scenario, the channel between the communication system and the radar receive antennas is fixed. So the matrix G2 is probably full rank, so it does not have a null space. On the other hand, if we, in the MIMO MC case, the channel changes on a symbol by symbol basis. So this random sampling basically modulates this channel, and it makes it have a non-zero null space. So this null space can be exploited by the communication system to transmit on that null space so that it interferes less with the radar. Here's some results on the effective SINR versus power budget for different schemes that use different levels of cooperation. For example, uniform precoding for the radar is a black line, and selfish communication, or null space precoding for the radar and selfish communication, and so on. And the red is the proposed joint design. And one can see that the joint design scheme outperforms all other methods in terms of effective SINR. We want the effective SINR to be high before we do matrix completion. And this is the relative target estimation RMSE for different methods. Again, the joint design scheme achieves the lower SINR. Sorry, the lower target estimation error. So these results were for a 16 by 16 MIMO MC radar and a 4 by 4 communication system. And here we compare the effective SINR in terms of the subsampling scheme performed at the radar. For the traditional MIMO radar, the black line, and the proposed using the red line. Now, when we sample all points, the two approaches are the same down here. Now, if we sample very few points, the effective SNR is high because we don't have a lot of noise. We only sample very few points. And then it drops as we sample, as we increase the sampling rate. But of course, if we look at the target estimation error, if we obtain a small number of points down here, we will have large error because the matrix completion does not work well. Turns out that the matrix completion works well, better than the MIMO, traditional MIMO radar, when the sampling rate is between 0.4 and 0.7. So when we sample between 0.4 and 0.7, we achieve better target estimation result than typical MIMO radar. So this work suggests that MIMO MC radar can coexist with communication systems and achieve better target RCS estimation than MIMO radar, while saving up to 60% in data samples. So our work that I presented so far assume that you have two systems, that they use two different platforms, and they cooperate in order to reduce interference to each other. But in many cases, we would prefer to have a single system that would perform both sensing and communication operations. And this is what the DFRC does. You may want to look at this tutorial level paper on DFRC systems. in autonomous driving applications, for example, it would be very popular such system, because while you're sensing for other vehicles and obstacles, you can also transmit information to other vehicles. So having one device, it would be very convenient. Now, there are many ways to embed communication information in radar waveforms. For example, this has been done by using the side lobes for modulating the side lobes to convey communication information, and using the main lobe for sensing. There have been also approaches where they embed information in the antenna activation pattern. I call those generalized spatial modulation type of approaches. And they have been used also for MIMO radar. And OFDM waveforms have been used for radar sensing. OFDM allow for high communication bandwidth, and they're very convenient for dealing with frequency selective fading with a channel. The way that the OFDM waveforms have been used for radar in the past does not exploit well the available bandwidth. For example, there are works that have been assigned antennas to blocks of subcarriers in an exclusive fashion, or there are works where they assign each antenna to one subcarrier only. So in that sense, they do not exploit all available bandwidth, and they cannot achieve high communication rate. So what I'm gonna present next is our work where we use the available subcarriers in a shared fashion. And in this way, we achieve high communication rate. So I have here a diagram. I'm showing two antennas that do OFDM modulation. For example, they do QEM modulation, perform IDFT, then parallel to serial conversion, and then they transmit. That's what each antenna does. Now, the receive antenna will demodulate. And for sensing and communication, we're going to use the demodulation symbols. So DT, I denote the symbols at the transmit antenna, and DR are the symbols at the receive antenna. So each symbol has three indices. M is the antenna index, I is the carrier index, and mu is the OFDM symbol index. So suppose that we have NS OFDM subcarriers, and we have NT transmit antennas and NR receive antennas. And there are NK targets out there, and its target is characterized by angle theta, range R, and Doppler frequency F. Let's see how we can use the received symbols to estimate the angle of its target. So let's look at the nth receive antenna after sampling and performing an S-point DFT. So we have the D sub R symbol, the receive symbol. It can be expressed as we see it in this summation. So it's the contribution of NK targets. And in here, we have the signal that was reflected by the targets, and the signal was transmitted by the NT antennas. So we have a summation over N. N is the index of the transmit antennas. And if there was one antenna per carrier, this expression would have been much simpler, because this summation would not exist. It would be just one term. And it would have been a lot easier to estimate the angles. But the fact that we have this summation makes things more complicated. But still, let's see how we can estimate the angles. we can view this double summation as a summation over K of some quantity A that depends on K, subcarrier index and OFDM symbol index mu, times e to the j omega m, where omega is whatever is shown by red in this equation. So the omega depends on the angle of the target, and the index, the subcarrier index I, and m takes values from 1 up to nr, the number of receive antennas. So you can view this, the received symbol, as a summation of NK complex sinusoids. So you can apply any method that you want to find the peaks of those sinusoids. For example, you can take an NR point DFT of the received symbols, NR meaning across all receive antennas. And if you do that, you will see peaks, and the peaks will indicate the omegas, the omega Ki. And going back to what omega Ki is, you will get the theta K, that is the angle of the target. Now that we have the angles of the target, we can look inside each angle. You can have multiple targets inside that angle beam. So if we look at the amplitude of its frequency that we found before, in other words, the A quantity, if we look closely, this quantity can be expressed like this summation. And if we extract whatever we know so far, or whatever we have estimated, which is the angles, we get this A prime term. And the rest is a summation like this. NQ is the number of targets that exist in that angle beam. And we can divide A by A prime, and then we're just left with this summation. And again, you can see that this summation of as function of I is basically a sum of sinusoids, complex sinusoids. These are the complex amplitudes, and the frequencies of the sinusoids relate to the ranges of the targets that are found in that angle beam. So if I take a DFT and NS is the number of carriers, a point DFT along I will see peaks, and the peaks will give me the ranges of the targets. Similarly, looking at the same summation, I can see it as a complex sinusoids with frequency that's proportional to the Doppler frequency, and these are the complex amplitudes. So if I take a Fourier transform along mu is the OFDM symbol, so I need multiple OFDM symbols. If I take the DFT along that, I will see peaks that will give me the Doppler frequencies of the targets. So although I'm using all carriers in a shared fashion, so far I showed you that you can estimate the angles of the targets and the Doppler and the ranges of the targets. Now, looking at the communication receiver, assuming that the number of transmit antennas is smaller than the number of receive antennas at the communication receiver, if you look at the ith carrier, then you have an expression like this. HI is the channel frequency response along the ith subcarrier, and AI contains all the symbols transmitted by on carrier I. All antennas have contributed on carrier I. So assuming that you know the channel, you can recover the transmitted symbols. So in this way, NS, and number of carriers, times the number of transmit antennas, this is how many symbols are communicated per channel use. So this is very fast communication rate. we fully exploit the available bandwidth. But on the other hand, the sensing resolution depends on that NR point DFT that we do. Like NR is the number of receive antennas. So it depends on the physical size of the receive arrays. Now, the other schemes that have used OFDM waveforms, by not allowing antennas to share subcarriers, they maintain orthogonality of the transmitted waveforms. So at the receiver, they can exploit that orthogonality to synthesize a virtual array and achieve resolution higher than NR. So in this case, by achieving this high communication rate, I'm not getting as good of a sensing resolution. But let's see how we can change that. Maybe if we do a small sacrifice in bandwidth, we can improve the sensing resolution. For example, suppose that only NX antennas are active, and we assign carriers as follows. There is a group of shared carriers, and there are NX private carriers. So these NX carriers are assigned to the active antennas in an exclusive fashion. So the blue has this private carrier. It transmits, only the blue transmits on this carrier, but it transmits on all shared subcarriers, and so on. So we pair antennas, active antennas, with carriers. So the antenna N is assigned with private subcarrier IN. Now, over the private subcarriers, we have waveform orthogonality. So if we look at the receive symbol, there was only one antenna that contributed to, or one transmit antenna that contributed to that symbol. So the receive symbol on the private carrier IN is looks like this. If we take these receive symbols for all private carriers and on all receive antennas, we can formulate a vector that can be expressed like this. So this is a summation over nk, the number of targets. Here we have a Kronecker product of the transmit and receive steering vector of the array. And D is a diagonal matrix that depends, has the ranges of the targets in there. Kronecker product, a diagonal matrix. And the beta k's depend on the Doppler frequency. So this looks like a sparse virtual array. And we could exploit that to obtain the angles with much higher resolution. So how do we do that? We discretize the angle space on a grid of n points, and considering the range space that we have already estimated based on the private subcarriers, let's say the ranges 1 up to R and K, we can formulate this, we can rewrite the previous equation in terms of an overcomplete basis. And the beta tilde here are non-zero only if there is a target at range RL and angle bin theta K. So to construct this basis, basically we need to know the ranges that we have estimated based on the private, based on the shared subcarriers. So this is sparse signal recovery problem. We can solve it and find the beta tilde coefficients that will tell us where the targets are and give us higher resolution angles. Now, if we look at for the communication system, if NX is smaller than the number of receive antennas at the communication system, then the receive symbols on the ith carrier can be expressed like this. HI now will be a sparse vector. It will contain the symbols transmitted over the ith carrier. And we can estimate this vector, these symbols, using sparse signal recovery techniques. We can also use this equation to identify, based on the support of AI, to identify the active antennas. And once we identify the active antennas, then we can recover the symbols using like a least squares approach, focusing only on those active antennas. Now, there's another way that we can convey information in this scenario by looking at the activation pattern of the antennas. If we have NT antennas and NX are active, there are NX choose NT different activation patterns. And then we can transmit the symbols on the NS minus NX shared subcarriers, and then times the number of active antennas, plus the log base 2C position bits due to varying the active antennas. We can also use different reordering of private subcarriers to increase the position bits. In this scheme, we want to use a small number of RF chains because we want to also reduce the cost of the system, the complexity of the system. So to summarize, for the fastest communication speed, all antennas are active, all antennas transmit on all carriers, and we showed that we can communicate NX times NS symbols in each channel use and achieve angular resolution NR, the number of receive antennas. To improve this angular resolution, we showed that we can use a small number of private subcarriers NX equal to the number of active antennas. And we're going to use these subcarriers to formulate a virtual array. In this way, we achieve this rate, NS minus NX plus 1 times NX, these many symbols in each channel use. So basically, each antenna has NS minus NX private shared subcarriers and one private carrier. And we have an X antenna, so it's this product, the number of symbols that are transmitted in each channel use. And the angular resolution based on the virtual array is equal to this, which is much larger than NR. Now, we can do more if we want to, in what I just presented, we transmit an omnidirectional beam. But we may want to formulate a certain beam. For example, we want to formulate a very focused beam on the communication system and like a wider beam looking for targets in certain direction. So if we want to do that, then we're going to have to use pre-coding. So I'm going to discuss now how we do that using optimally designed precoder P. And by optimally selecting the antennas, and I will use an antenna matrix, selection matrix S. So selecting antennas will also help us meet a certain beam pattern. So going back to the system that I showed you in the beginning, suppose that we have two RF chains, and Q are the QEM symbols. We're gonna distribute those Q symbols to 2 out of 4 transmit antennas. And we're gonna do that based on the antenna selection matrix S, and we're going to also do some pre-coding P. So the symbols that we will transmit eventually can be expressed as this. S is the selection antenna matrix, P the precoding matrix, and Q are the symbols before the precoding. And each symbol has indices, again, antenna, carrier, index, and OFDM symbol index. So if we look at the baseband received signal, so far I did not consider the channel. In this case, I will also consider the channel coefficients and see what is their effect. So if we look at the received signal at the mth antenna over the ith carrier as function of time, it's going to be the echo out of k targets, and each echo will look like this. So it's going to be the signal that was transmitted, delayed by this tau amount, and multiplied by this coefficient that is function of the transmit, the receive antenna, and the target, right? So this beta and this tau represent the effect of the channel between transmit and receive antenna. So the tau is given by this form. It depends on the range of the target and this quantity and the angle of the target. Now we're going to make some assumptions to make things simpler for this beta tilt quantity. So this beta tilt basically is the effect of, it's like a multiplicative scalar between the transmit antenna, the target, and back to the receive antenna. Because our transmit antennas are spaced far from each other, we're going to select them, randomly select them. We will take that this term does depend on the transmit antenna, but because the receive antennas are all closely spaced, we're going to assume that this scalar is the same for all receive antennas. So also because the subcarriers are closely spaced, this beta does not depend on the subcarrier index. So based on these assumptions, the channel coefficient is only, we assume it only depends on the transmit antenna and the target. It looks like this. So if we look at the received symbol, is given by this expression. Again, we have the channel coefficient here. Again, we can represent it as a summation of k terms. K is the number of targets. And we have k complex sinusoids here. Their frequencies are the omegas, exactly as before. And their amplitudes are the A's. And again, and the channel coefficients are in this and angle, and they can be represented by this summation as we had before, except now that this A prime term contains the channel coefficients. Although I did not need the channel coefficients for the frequency, for the angle estimation, I have them here, and I need them in order to estimate the range and the Doppler frequency. And let me assume for a moment that I know these channel coefficients. I will show you that we can actually estimate them. So assuming that we know them, I can perform IDFT. I can perform a DFT based on the carrier index I, or based on the OFDM symbol index mu. And based on this, I can find range and Doppler. I can use again the private subcarriers to improve the angle resolution, the target angle resolution, exactly as I did before, except that now the virtual array will be slightly different because of the precoding and the antenna selection matrix. It's going to be given by this form that looks like a virtual array, but it's not. It does not correspond to a uniform linear array, but in terms of structure is similar, and I can still use it to obtain target angles with much higher resolution using a sparse signal recovery approach. So to formulate this, again, I need the ranges that I have found already using the shared subcarriers. It turns out that I can use an iterative scheme to improve the resolution or the angle resolution of the targets. So I start with the coarse angle estimates based on the shared subcarriers. I obtain the range estimates. Because I start with coarse angle estimates, I may miss some targets, so I may end up with fewer range estimates. I still use these range estimates to set up the sparse signal recovery problem on the private subcarriers. The solution will give me new angles that will be much higher resolution than what I started with. I will use those to re-estimate the ranges. And I keep repeating that, and it turns out that I can significantly improve the resolution. Now, how do I estimate the channel coefficients? Suppose that periodically I assign antennas to group of subcarriers in an exclusive fashion. And based on those subcarriers, if I look at the estimated angle bin, I can get an expression like this, where again, I can view this as a summation of complex sinusoids whose amplitudes depend on the channel coefficients and the Doppler frequencies. The Doppler frequencies can be pre-estimated based independently based on the private subcarriers. And then I can come back here and based on the amplitudes, I can estimate the channel coefficients. Looks like I'm running a little bit behind in time. Now let's talk about design of this antenna selection matrix and the precoding matrix. I can look at the sparse array output in direction theta, and you can see that it looks like this. This is the steering, transmit steering vector at antenna theta, and using the carrier I, and F is the inverse Fourier transform matrix. I can find the power in that direction that looks like this, and the Ri here can be viewed as the covariance matrix of the Qi, which is the symbol before the precoding. I can look at the power of the received signal over all subcarriers at the communication system, and looks like this. Hi is the channel, and I can find the SNR at the communication receiver. Again, it's a function of P, S, and the channel. And the criterion that we used to design the S and P was we defined this loss function that is basically the error between the achievable beam pattern and a desired beam pattern, P. It's a weighted combination of the beam pattern error, the SNR at the communication receiver, and also this that ensures that the S that I'm going to find will meet the properties of a selection matrix. So I'm going to minimize that with respect to S and P. And we did the minimization using learn to select type of approach, which is a learning approach that uses a set of separate softmax neural networks. Each row of the matrix S is found by a separate softmax neural network. So this is how the softmax network output looks like. And we used this type of iteration, alternatively estimating P and S. First, we fix P and optimize the criterion with respect to S. And then we fixed S and optimize with respect to P. So to show you some results, we considered an OFDM system with center frequency, a radar system with center frequency 24 gigahertz. It had 512 subcarriers. The total transmit antennas were 32. 16 was activated. The number of receive antennas were 64. And we wanted to design this kind of beam pattern, so using 16 out of 32 antennas. And we assumed that the SNR was 15 dB, and there were 4 point targets at these angles, 42, 42, two targets at the same angle, and the rest are different angles. So if we apply if we try to estimate the angles based on a DFT across the receive array, we get this peak, the blue peak. It doesn't hint in the presence of 3 different angles. It's just one because of the low resolution. But if we apply what I presented using the private subcarriers, since we have 16 active antennas, we have 16 private subcarriers. Based on that, we can clearly, and apply sparse signal recovery approach, we can clearly see the 3 peaks corresponding to the 3 angles. So if we do the iteration, as I said, we start with the coarse angle estimation, where we find just one angle here. Then based on that angle, we obtain 2 ranges based on that angle. Then we use these 2 ranges to set up the virtual array, apply sparse signal recovery method. We find 3 ranges, 3 angles now. So we keep repeating that, and after 6 iterations, we have found all angles and all ranges. I guess in estimating the range, I said that we need to know the channels. Well, we simulated the channels with certain variance, mean 0.1 and variance 0.01. And this is the estimation result. When we ignore the channels, we can still find the peaks that indicate 2 ranges that we're looking for. And this is the result when we use the channel estimates. It's much smoother graph. But even in this case, you can find the correct peaks that give you the ranges. Now, looking at the SNR gain at the receiver, we can see that depending on the number of transmit antennas, we get different SNR gains. The smaller the antenna, the active antenna number, the higher the SNR gain. And this is because we use sparsity in order to find the active antennas and then obtain the symbols. So the fewer the active antennas, the better our estimation is. Also, the smaller number of the active antennas, the better selection we can make among the available antennas. And by selecting the antennas, we basically select the channels to the communication receiver, so we get better performance. This is a graph that shows the probability of finding the correct selection matrix versus SNR. Again, for the fewer active antennas, the success rate is high even at very low SNR. While as we increase the number of active antennas, the success rate becomes higher at higher SNR. And this is the bit error rate. Again, the bit error rate is the best when we have a smaller number of antennas. So for this example, the maximum bit rate of the system was 1.638 gigabits per second. And the loss of the bit rate because of the use of private subcarriers was 0.096. So it's probably a small price to pay in order to achieve good resolution. So to conclude, we presented a MIMO radar with sparse sensing and matrix completion, and showed that MIMO MC radar can reduce the number of data required without hurting the MIMO radar performance. I showed you a co-design of MIMO MC radar and MIMO communication systems, and so that the random sampling modulates the interference channel and facilitates the co-design. And I also presented a new DFRC system that uses wideband MIMO radar that transmits OFDM waveforms. And the system can achieve high communication rate, high range resolution, because it uses all the available bandwidth. By a small reduction in bandwidth, it can achieve high angle resolution via the use of private subcarriers and a virtual array, and also achieves low cost because it uses a sparse array. And this concludes my presentation. I'll be happy to answer any questions. Sorry, I went over time.
Hi, Athina. So yeah, very impressive talk. So I've received a number of questions, and so I will name some of the interesting, questioners to ask their questions. So the first question is come from Chandra Murthy. So Chandra, can you please unmute yourself and ask your question?
Fan, thank you very much. Yeah, my question is on slide 35 in your previous deck. But before that, first of all, thanks very much for this lovely talk. My question is on this slide 35.
On this one?
Yeah. I think this is the one. Yeah. And so we have figured out the Doppler frequency and the range, but how do we know which Doppler frequency to associate with which range? Yeah, these two steps, right? You have the Doppler and the range, but you need to make an association of the Doppler to the range.
So we look at the angle beam in theta k, and we find two peaks. And you're saying which?
Yeah. If there is one peak at theta k, then it's fine because there's a unique peak, and that corresponds to the range and Doppler for that theta k.
Right. I guess for the Doppler frequencies, you can find them looking at the private subcarriers directly. You need one carrier to find the Doppler and maximum OFDM symbols. Right. So you can correlate with that.
Okay, right. I got it. Thank you.
Thank you.
Okay, thank you, Chandra. So our next question is from Perry Wang. So Perry, can you please unmute yourself and ask?
Yeah, can you hear me?
Yeah, we can hear you.
Hi, Professor Petropulu. So this is really an interesting talk. So actually my question is regarding actually also the DFRC. So if you want to use all the bandwidth, let's say in a 76 to 81 gigahertz, so I guess the requirement for the OFDM, like when you're sampling the OFDM waveforms in the receiver side, it probably requires a lot of sampling rate, right? So yeah. I'm just curious, like when you compare, the OFDM with the current like automotive radar system using FMCW. So it seems to me the sampling requirement is much higher for the OFDM, as well as FDM in the communication side, you have the PAPR issue. So yes. I'm not sure. So I think my question is, could you comment on the both like a sampling requirement and the PAPR issue when you consider this OFDM DFRC system?
Yes, you're right. That there are these issues when using OFDM systems. But I guess there have been papers suggesting that there are clear advantages of using OFDM despite these issues.
Right. Definitely, I think you can do much better job, right? More functionality compared to the traditional automotive radar.
So I guess it remains to be seen in practice how practical this approach will be, because as you say, there are issues.
Right. Yep. Thanks for the talk.
Mm-hmm. So if I may go back to the previous question, I thought if you get a range estimate and you go and formulate the SSR, the sparse signal recovery problem, then you can see which frequency is matched to which range, right? So you cannot miss the matching.
Mm-hmm. So this is the answer for the previous question by Chandra, I think, right?
Right.
Okay, thanks, Athena. So I think our next question is about the beam pattern design. So this is asked by Yongzhi Wu. So Yongzhi, can you please unmute yourself?
Okay. Can you hear me?
Yeah, we can hear you. Yeah.
Okay. Thank you, Professor. I have a question about the loss function of beam pattern design. In the loss function, the third term is inverse SNR, right?
Yes, because
I have a question. Is it reasonable to use the log scale SNR at the third term, since the log scale inverse SNR value may be negative?
Yeah, because we want to maximize that, right? So we want to minimize negative.
Because I think the first term and the second term are all non-negative.
Yes, so we want to minimize the first two terms and we want to maximize the third term, or minimize the inverse of the third term.
Yes, I mean the third term may be negative. I think the loss function should be a positive function.
Why? I mean, if we want to minimize that, so that's why it is negative.
It can be negative, right?
Yeah.
Oh, okay.
Yeah, so I guess it can be negative, because you are minimized a negative one, then you are maximized, right? You're maximizing.
Yes. Yeah.
Okay. Thank you, Professor.
So our next question is from Yanis about the number of antennas, I guess. So Yanis, please, can you unmute yourself? Yanis? Hi, Yanis, are you with us? Hello? Okay, I guess Yanis is not with us now. So okay, and then I think I have a final question. So can you hear me?
Yes.
Yes. So I have a final question about your technique of the private subcarrier and the shared use of the all the other subcarriers. Can you please go to that page? I think you have a figure for that. Yeah, the next one, yes. So it seems to me that, I mean, the figure of the antennas.
I
think it's the next one, maybe. I know the previous one, so lots of antennas. So that, this one,
This
the private subcarriers and the shared subcarriers. So there's a figure for that, I think. Yeah, exactly.
Okay.
So I guess you are using these private subcarriers, which are located to these antennas, so exclusively. So yeah, in that sense, you can have orthogonal waveforms, right, with this private carrier.
Right.
And with these shared carriers, you can transmit the information at a higher rate, right? I guess. So I'm wondering, can you also transmit information by using these private carriers? For example, by exchanging the order of these carriers to represent some fingers.
Yes,
right?
exactly.
Some symbols. Yeah.
Yes,
so maybe in that case, you can again improve your communication rate.
Right. I did mention that we can do different reordering.
Yes. So in that case, okay, yeah. That would be great. So in that case,
I did not use those when I gave you numbers for the achievable communication rate, but definitely you can do all this.
Yeah. Very interesting. Okay, so we have another I think a general question from Joachim. So Joachim, can you please unmute yourself?
Yes, can you hear me?
Yeah, we can hear you.
Yes.
Yeah. I was just curious, since you're doing research in this area, if you know what the state of commercialization. Are there any chips built for unlicensed or licensed spectrum? To what extent are things actually being built for joint communication radar at this stage?
So I don't think there is anything available right now, but I know that several companies are looking into this. And this is why, Fan had somebody from Huawei.
Yes, right.
First day of this seminar, who said that they're very interested in deploying these systems.
But so it's Huawei, then it would be even for licensed spectrum in that case, or?
I'm not sure.
Mm-hmm.
Probably the unlicensed spectrum.
Yes.
All right. Thanks.
Okay, so I think the final one, Yanis is back now, so he wants to ask the final question. So Yanis, please unmute yourself. Hello, Yanis. Hello. He's away again. So maybe I will ask the question on behalf of him. So he's asking on the slide 25 to 26, if the number of antennas is made very large, I think it's next final one, I think.
Okay.
Yes, in the next part, yeah.
Yeah, it's on the second deck. Apologies.
Okay, yes. You're here finally. Okay, so yes. You can ask you by yourself.
Thank you, Fan. Thank you, Professor Petropulu. I would be expecting, if you take the number of antennas to be very large, to have a sweet spot type behavior, but here it looks it's monotonely improving. shouldn't there be like kind of a sweet spot if you take the number of antennas, the NX, to be very large, like take it to infinity?
Well, you have NX, you select NX out of NT. You have a number of available antennas and you want to select a small group of those, right? So the maximum that you can get is NT, the available antennas.
So if you take that, if you take, let's say, both NT to be very large and NX to be also very large, is there any sweet spot relation between NX and NT then? I guess that would be my question. Like if you choose NX to be too close to NT and that's very large, that may create the bit rate to go down. That's
so
my intuition.
When you do that, you don't have flexibility to select the channels. Maybe some channels are bad. Some communication channels are bad, right? Each antenna is facing a different communication channel to the communication receiver. So if you have more flexibility to select those channels, you get a better rate, right? Because eventually you have to recover the symbols. If you have like deep fading over some channels, it's good to avoid them.
I see. So there wouldn't be ever any issue of having too much interference by selecting too many, by making the NX too high.
No, I don't think so.
Okay. All right. Thank you.
Thank you.
Okay, thank you guys. I think that would be the final one. So thank you again, Athina, for giving us this wonderful talk. And I would like to advertise our next event. So Athina, can you please, stop the sharing the screen?
Thank you very much.
Yeah. Okay, so our next event would be our 5th seminar. So the speaker will be Professor Gerhard Feitwis from TU Dresden from Germany. So this will be again a virtual seminar, which will be held on July 13. So 2 weeks later. So please stay tuned, and we'll send out all the information of this talk. Okay, thank you guys. And I think that is the end of today's seminar. Thank you. Bye-bye.
Thank you very much. Bye.
Bye, Athina.